Let's continue talking about heat and energy. Heat or thermal energy is a type of energy that flows from warm objects to cool objects. So again, we're coming back to that concept that heat energy flows from warm to cold. Always. It always flows from warm object to cool object. The thermal energy of a substance is determined by the movement of the molecules. So if they're moving faster, then it's a higher temperature. Also, the kinetic energy feeds into that. Heat energy is transferred from a warm object to a cool object by the movement of molecules. So temperature, remember, it's a measure of the average kinetic energy of molecules. We've talked about that before. So let's look at these sentences and see if we can kind of fill it in. The faster the particle moves, the higher the kinetic energy it has. So since it's moving faster, it has a higher kinetic energy, the temperature is higher. Okay. Now the slower the particle moves, the lower the kinetic energy, and thus the temperature is lower. Temperature and kinetic energy have what type of relationship? They have a direct relationship. All right, and then we've got a couple examples. Pause the video right here, see if you can figure this out. We want to draw an arrow for each of these pairs of objects that we're giving you the different temperatures, and draw the arrow to show which way the heat will flow, the direction of thermal transfer, or which way will the heat flow. Okay, remember, heat always flows from warm object to cool object. So what we would have with this one, I've got a warmer object, 60 degrees, cooler object, 40. So the heat's going to flow that direction, from 60 to 40. With the next two objects, it might be a little tricky. You may have kind of fallen for this. This is a negative number, which means it's lower than the temperature in Celsius. So warmer object to cooler object, it would flow this way. Heat is going to flow from 0 degrees Celsius to negative 15. So higher temperature to lower temperature. Now we have 9 and negative 19. Negative 19 is a lower temperature. So it'll flow that way. And then finally, we've got this one, 55 and 55. Now some students would maybe look at this and say, temperature's not going to change, heat's not going to flow. That's not a terrible answer. But a better answer is that heat flows at the same rate in both directions. So we do have some heat flowing, we have some transfer of energy between the two, but since they're the same temperature, there's no net change. We have the same amount of heat flowing upward and downward, so to speak, if these objects were stacked. All right, looking at thermochemistry a little bit more, so not just thermodynamics, which is the study of heat, but we want to talk about something called thermochemistry, which is the study of heat changes that accompany chemical reactions and phase changes. So heat change and chemical reactions and phase changes. To study the amount of heat absorbed or released, we first have to define the system, surroundings, and the universe. This may seem a little bit unnecessary to some people, but it is really important in order to be able to actually answer these questions effectively, including some of them that initially seem simple. You really need to think about what the system is, what the surroundings are. Okay, so here's our definitions. Here are our definitions. The system is the chemical reaction or the phase change being observed. It's that specific thing we're focusing on. Chemical reaction or phase change usually. The surroundings, or the surrounding, is everything around the system that's involved. So everything that is around the system, everything else actually. And when we say the universe, we're talking about universal. That's everything. It's everything at all. It's both the system and the surroundings. In other words, it's everything. Now, we can't normally think about everything in the entire universe or evaluate everything in the entire literal universe when we're doing this. So we kind of think in a little bit narrower scope. What are the things, when we talk about surroundings, we mean the things that are in kind of direct contact or very near contact with our phase change or chemical reaction. We're going to look at an example down here. So we've got a diagram down below. We've got a beaker with A, B, C, C, A, B. We've got some different letters in here, and those each represent atoms or molecules that are floating around in a solution made with water. Okay. So observing this diagram showing the reaction of A plus 2B yields C. So there's our reaction in an aqueous solution. By the way, I hope that you already know this. We have talked about it, but just a reminder, aqueous solution. Aqueous means dissolved in water. Now, if it's dissolved in water, if it's already dissolved in water, that's not a chemical process, it's a physical process. So just keeping in mind, the water's not involved in this chemical change. So let's look at our system. What is our system? Our system is just A, B, and C molecules and their interaction. It's the chemical reaction. You could also define the system as A plus 2B yields C, if you'd rather write it that way. But the concept is the only thing that counts as the system is A, B, and C, those molecules that are interacting inside the solution. So what does that make the surroundings? Well, anything that is around those molecules. So that includes the table that this beaker is sitting on. And think through it yourself. Think through some of the things that might be included. You might think of something I don't. The table, the beaker itself. If the scientist was holding it in his hand, you know, possibly the scientist who's doing the experiment. I see a little stir rod in there, the stir rod. If I were to put a thermometer in there, the thermometer would be part of the surroundings. I see that there's air coming in contact with the surface. So air is part of the surroundings. And also, because I know it's dissolved in water, water is also part of the surroundings. Okay? That's what the surroundings are. And the universe is everything. It's the surroundings, it's the system, plus surroundings. Okay? In other words, it's A, B, C, table, beaker, etc. And I could go on and on and on. Everything we named, system and surroundings, is all part of the universe. Okay. Now, last thing I want to mention to you here is why this is valuable, why this is important. When we're thinking about heat transfer, where the heat is going to flow from or where it goes to and that sort of thing, we really need to think about whether we're focusing on the system or the surroundings. What is our system? So for this example, if I wanted to say that the system releases heat, that means that the surroundings would absorb the heat. Okay? So if the system releases heat, that means that it's getting rid of heat. Its temperature would decrease. But the surroundings would be absorbing that heat. Their temperature would increase. Okay? Now, let's say that the system, this chemical reaction, is absorbing the heat. If it's taking it in, it's absorbing it. Well, where is it going to get heat from? Where is it going to get the energy to absorb the heat? It will absorb the heat from the surroundings, which means since that heat is being taken away from the surroundings temperature will decrease. We're going to talk about that a lot more in the next video.